Welcome to the deep dive. This is where we get our hands dirty with dense technical source material and pull out the essential knowledge that really defines advanced engineering.
Today, we're focusing on precision machining. This is really the foundational process for any high-stakes industry you can think of. Aerospace, medical, high-performance automotive.
Yeah, if it's durable and accurate, it probably started here.
It absolutely did.
So our sources for this deep dive are split into two, I'd say, high-tension categories. You've got
Yeah.
the sharp edge, and then you have the immovable hold.
That's a great way to put it. We're analyzing everything from, failure modes and exotic materials for cutting tools, all the way to the physics required to hold a huge workpiece perfectly still.
And our mission here is to uncover those critical engineering trade-offs, the ones you have to make to keep accuracy up and production time down.
We're going from Taylor's equation and the metallurgy of cemented carbide right through to the 3-2-1 principle of work holding, and then seeing how it's all validated with modern simulation.
Let's start with the tools then. It's sort of a weird reality, isn't it? That no matter how perfect the machine is, the tool itself is, well, it's designed to fail.
It is. The whole goal is just to control how and when that happens. Our sources lay out three main ways a tool fails during, smooth economic machining.
And only one of them is actually okay.
Right. The first two are complete disasters for production. You have to design them out. First up is mechanical breakage.
That's the sound that makes everyone on the shop floor jump, the tool just shattering.
Exactly. It's catastrophic, often random, caused by excessive forces, a shock. It stops production cold. And it usually ruins the workpiece.
Okay, what's the second no-go?
That would be plastic deformation. This is where intense stress and high temperatures cause the cutting edge to literally flow or soften.
So it doesn't chip, it just sort of melts at the edge, it starts flowing like soft putty and loses its shape.
Precisely. It's a rapid dulling, and it's completely unacceptable. So that brings us to the third type, which is the one we have to live with. Gradual wear.
The inevitable decline.
It is. It happens on the flank and the rake surface of the tool. You can't prevent it, you can only slow it down. The entire engineering effort is basically preventing the first two and just managing the rate of this third one.
So if a tool doesn't explode or turn to mush, how do engineers know when it's officially worn out? What's the metric?
Well, in a controlled R&D setting, it's very specific. Failure is when the average wear on the flank hits, say, 0.3 millimeters.
Tiny.
Oh, very. Or when the crater wear, that's the little scoop behind the cutting edge, reaches 0.15 millimeters. These are the points where you start losing surface finish or accuracy.
But on the factory floor, it's a bit more sensory, right? You're not measuring with a microscope in the middle of a job.
Not at all. The operator is listening. Failure is often signaled by excessive vibration or an abnormal high-pitched noise we call chatter.
I've heard that sound. It's awful.
It's a self-excited vibration, and it's a direct sign something is wrong. That, or the part, simply starts measuring out of tolerance. That sound is an immediate alert.
Okay, let's get into the mechanics of that gradual wear. What is actually happening at the atomic level to degrade the tool?
There are four key mechanisms here. The first is pretty straightforward. Mechanical wear. That's your basic abrasion, chipping, adhesion, just physical rubbing and tearing.
But I'm guessing it gets more complex when you add the extreme heat of cutting.
It does. The real heavy hitter, especially when you're cutting fast, is thermochemical wear. You can just call it diffusion.
Diffusion, so material is actually moving from the tool to the part.
To the chip, actually. At these high temperatures, atoms from the tool material literally start to migrate and transfer into the chip that's flowing over the tool face.
So you're losing your tool atom by atom into the stream of waste material.
You got it. And the rate of this diffusion just skyrockets with temperature. It's the main problem when you're using high cutting speeds or machining really tough materials that generate a ton of heat.
What are the other two mechanisms?
There's also simple chemical wear if the tool material isn't stable, and the much rarer galvanic wear, which is an electrochemical process. But diffusion is the big one.
So to survive all of that, a tool needs a set of properties that, frankly, sound almost contradictory.
They really do.
Yeah.
You obviously need high strength and fracture toughness. You need extreme hardness for abrasion. But the real engineering magic is in achieving high, hot hardness.
Hot hardness. Or red hardness, I think I saw.
Same thing. It's the ability to resist that plastic deformation, that flowing putty effect, even when the cutting edge is at 800, maybe even 1,000 degrees Celsius.
That's white hot. That's just incredible.
It is. And then there's the thermal contradiction you mentioned, which is fascinating. The material needs to have low thermal conductivity right on the
In fact,
surface.
like a heat shield.
Exactly, to block heat from getting in. But some heat will always get through,
Yeah.
and the core of the tool needs high thermal conductivity to quickly pull that heat away from the cutting edge and dissipate it.
How is that even possible in a single material?
It's not, really. That's why we rely almost entirely on composite materials. Which brings us to the workhorse of the industry, cemented carbide.
Okay, so how does this composite solve that thermal puzzle?
Cemented carbide, or WCCO, is a product of powder metallurgy. You take super hard tungsten carbide grains, the WC, and you press and sinter them inside a matrix of tough metallic cobalt, the Co.
So the tungsten carbide is providing that insane hardness and wear resistance.
Correct. And the cobalt binder is like a shock absorber. It provides the toughness to keep the super brittle tungsten carbide from just shattering on impact. It's this combination that gets you hardness levels up to HRA 88 to 94.
And the genius is in tuning that recipe, right, by changing the amount of cobalt.
That's the core trade-off. If you use low cobalt, maybe 3 to 6%, you get the absolute highest hardness and abrasion resistance. But it's brittle. So that's for finishing, for micro tools where impacts are low.
And if you crank up the cobalt,
If you go to high cobalt, say 10 to 30%, the material becomes much, much tougher. It has great impact strength. So that's for heavy roughing interrupted cuts, even things like mining buttons that get hammered all day.
so a machine shop must have drawers and drawers of different inserts just for subtle changes in a job.
Oh, absolutely. The tool strategy is defined by these subtle changes. And we haven't even talked about coatings. Even tungsten carbide has a weakness. It oxidizes above 600 degrees C. So for high-speed work, coatings are essential.
And our sources point to two very different strategies there, depending on what you're cutting.
Yes, because the failure mechanism you're fighting is different. For steel, at high speed, heat and diffusion are the enemy. So you use a coating like TL or LCRN. These create a thermal barrier that gives you protection up to 800 degrees C and beyond.
But for something like aluminum, heat isn't the main problem, it's stickiness.
Exactly. Aluminum loves to weld itself to the tool face. We call that a built-up edge, or BUE. So for non-ferrous materials, you use ultra-low friction coatings. Something like DLC, which is diamond-like carbon, or TPOs, they're so slick that the aluminum just can't stick.
All right, let's shift from the material science of the tool to the process engineering of the cut. How do we actually control the life of these amazing tools? This brings in the math.
It does. A tool's life, which we call T, is mostly governed by your cutting parameters. But there's a clear hierarchy. Our sources confirm that velocity affects tool life the most, and depth of cut affects it the least.
This is defined by Taylor's tool life equation, which looks simple. VTN is mostly CN. What are VT and especially N telling us?
So VILR is your cutting velocity, $2 is the tool life in minutes, and $2 is a constant for that specific material and tool setup. The exponent, that's the critical part. It's a constant that tells you how sensitive that tool's life is to a change in speed.
So a small n means you're really sensitive to speed changes.
Very. A tiny increase in speed will cause a huge drop in tool life. A larger N is more forgiving. That number really dictates your whole production speed strategy.
Now that's the simple version. The sources mention a modified equation that adds in feed and depth of cut, but it still holds that the velocity exponent is the biggest. Why is velocity so much more destructive than, say, just taking a deeper cut?
Because velocity is what drives heat generation. The faster you go, the more friction, and the temperature at the cutting zone just rises exponentially. And since we know diffusion and deformation are driven by temperature, speed just accelerates failure way faster than taking a deeper cut, which mostly just increases the mechanical force.
Let's quickly define those two main variables a programmer is tweaking: speed and feed.
Sure. Cutting speed, V, is the surface speed of the workpiece, measured in meters per minute, or SFM. It controls the heat and therefore the tool wear.
And feed rate, FR.
Feed rate is how fast the cutter is advancing. Think distance per revolution or distance per minute. That dictates your material removal rate, how fast you're getting the job done, and also the chip load.
So the math gives you a starting point, but the sources are clear that the final tweaking that happens on the shop floor.
That's the art of the cut. Absolutely. The programmer gets you in the ballpark with the math, but the operator fine-tunes it using what they call the sights, sounds, smells, and temperatures. They're listening for that chatter, that vibration, and they're looking at the chips. You want small, broken chips. That's the sign of a healthy, efficient cut.
Okay, we've spent a lot of time on the sharp edge. Now for the other half of the equation, the immovable hold. If your tool is screaming along at 1,000 meters a minute, The workpiece better not move, not even a tiny bit.
Not even a micron. This is where the 3-2-1 principle comes in. It is the absolute bedrock of manufacturing accuracy.
And the core problem it solves is that any free object in space has a lot of ways it can move.
It has 12 potential movements. We call them degrees of freedom, or DOF.
Yeah.
You have translation along the X, Y, and Z axes and rotation around each of those axes, both directions.
And the 3-2-1 rule is this beautiful, minimalist solution to lock down all 12 of those movements.
It is. It's the 6-point positioning principle. You start with 3 points that define your main plane, usually the bottom of the part. Those 3 points stop the part from moving up and down on the Z-axis and from rotating around X and Y.
Okay, so it's sitting flat. Now what?
Next, you add 2 points on a side plane. This stops the part from sliding along the X-axis and from rotating around the Z-axis.
And the final point locks it in.
The 1 point goes on the third plane, the thrust plane, and that stops the part from moving in the last direction, along the Y-axis. 6 points, all 6 degrees of freedom constrained. It's elegant.
Now, here's the distinction that I think trips a lot of people up at first. You have locators and you have clamps. They're not the same thing.
Not even close. This is a critical point. The locators, the 6 points we just discussed, they're the ones that must resist the cutting forces. They are positive stops.
So the clamps.
The clamps rely on friction. Their only job is to push the workpiece firmly up against the locators. If a clamp fails mid-cut, the locator should still be holding the part against the force of the tool.
And if you violate this 3-2-1 rule, you get what the sources call abnormality.
You do. Under-positioning is when you haven't locked all 6 DOF, so the part moves. That's a scrapped part. Over-positioning is when you accidentally restrict the same degree of freedom more than once.
Which can actually bend or deform the part, right?
It can. If your locators are misaligned by just a few microns, you can build stress into the part just by clamping it, which ruins the final product. That's why you use things like a round pin and a diamond pin to locate in one direction but allow for slight thermal expansional tolerance in the other.
This complexity is why modern engineering doesn't just build a fixture and hope it works. They simulate it first. We've got a great case study on this for an aluminum engine cylinder block.
This is a perfect example of the modern workflow. They used KFD computer-aided fixture design along with FEA, which is finite element analysis, to get it right digitally before ever cutting metal.
Let's define FEA quickly because it's so important here.
FEA is a simulation technique. You take a complex 3D model, like an engine block, and the software breaks it down into thousands of tiny, simple pieces called elements. It then solves physics equations for each tiny piece and reassembles the results to predict how the whole block will bend, stretch, or deform under real-world forces.
So in this case, the engineers modeled 2 different fixture designs to see which one was more stable.
That's right. The first design had 2 locating pins and 2 vertical hydraulic clamps. The second design had only 1 locating pin, but it added more clamping force with 3 vertical hydraulic clamps.
But before they could trust the simulation, they had to validate their inputs.
They did. They calculated the clamping forces from the hydraulic pressures, 40, 50, and 60 bar, both by hand and with the simulation software, ANSYS. The results were within 4.2% of each other. That's a great correlation, and it meant they could trust their force data.
Okay, so they ran the validated simulation. Which design won?
The results were really clear. The first fixture, the one with 2 clamps, was significantly better. It resulted in far less total deformation on the engine block. At 40 bar of pressure, the maximum deformation was just 0.0168 millimeters.
16.8 microns. That's what, a quarter of the width of a human hair? It's nothing.
It's incredibly small. So based on the simulation, they built that superior 2-clamp design, and then they had to prove the simulation was right in the real world.
How did they do that?
They used a dial gauge indicator, which is a physical high-precision measuring tool. This one had a resolution of 0.01 millimeters, or 10 microns. They clamped a real engine block at 40 bar and measured the actual deformation.
And the result?
The experimental measurement was 16.18 microns.
Wow. That's almost identical to the 16.8 microns the FEA predicted.
It's an astonishingly close result.
Yeah.
And it confirms the entire digital design and analysis process. They knew it would work before they even built it.
So what was the final recommendation for the shop floor?
Operate the hydraulics at 40 bar. It provided perfect stability against the cutting forces, and it kept all the stress and deformation well below that critical 16.8 micron limit. It was the data-proven optimal setup.
What a journey. We've really walked the engineering tightrope today. We've gone from the microscopic struggle inside a cemented carbide tool
Mhm.
all the way to using Taylor's equations to maximize its life.
And we've seen how manufacturing repeatability all hinges on that elegant 3-2-1 principle, now proven out by digital simulations that can predict movements down to just 16 microns.
And we saw how incredibly rigorous that process is for a fairly standard an aluminum engine block. So here's the final thought we want to leave you with.
Mhm.
If that much work is needed for an aluminum block, what happens when you move to next generation industries? Aerospace, sustainable energy, they're machining exotic, complex parts like a titanium turbine blade. If 16 microns is the limit for aluminum, how much harder is the FEA challenge when the thermal expansion of a material like titanium can be way more than 16 microns all on its own? You'd have to model the fixture and the part getting hot and growing dynamically during the cut.
What new positioning strategies do you need when the part itself is actively fighting to grow in your hands? Something to chew on until our next deep dive.
We'll see you there.